You are looking at the night sky, but what you see is not the present. You are seeing delays, fragments of history, light that left long before your world existed. And if you follow that idea seriously, if you allow yourself to stop thinking of space as distance and start thinking of it as time, then the sky above you stops being a ceiling and becomes a corridor stretching backward through billions of years. I want you to imagine we begin here, quietly, on Earth, with the familiar band of the Milky Way cutting across the darkness, a river of unresolved stars that feels immense until you realize it is only one structure among countless others. A galaxy holding hundreds of billions of suns rotating around a central gravity, well, that keeps everything bound. And somewhere inside that rotation, the sun drifts unnoticed, carrying you with it. Now pull away, slowly at first, and the constellations dissolve. The stars no longer fixed points, but a three-dimensional cloud, then a flattened spiral. And the Milky Way reveals itself as a rotating disk threaded with dust lanes and glowing star-forming regions, elegant and vast, yet already shrinking as we continue outward, leaving behind every star visible to human eyes, leaving behind the idea that this galaxy is special. The large and small Magellanic Clouds drift into view, irregular companions orbiting our galaxy. Then farther still, Andromeda appears, a massive spiral containing perhaps 1 trillion stars, moving toward us across intergalactic space. Its scale forcing you to recalibrate what large means. And even that begins to feel local as more galaxies appear. Scattered first, then clustered, then woven into patterns, thousands of galaxies suspended in darkness, each containing billions of stars, each star possibly hosting worlds, and yet between them stretches emptiness. So deep you could travel millions of light years without encountering a single sun. As we continue outward, the universe stops looking random. Galaxies align into filaments and sheets. Immense structures, shaped by gravity, acting over billions of years. Matter flowing along, invisible scaffolding formed by dark matter. Leaving vast voids where almost nothing exists. And from this vantage, the cosmos resembles a web more than a collection. A structure grown rather than scattered. The farther we move, the more the universe changes, because distance becomes time, and galaxies begin to look younger, less organized, more chaotic, collisions more frequent, star formation more violent, shapes irregular and unstable, and you realize you are not just traveling through space, but watching cosmic history unfold in reverse, moving toward an era when the universe had not yet settled, when matter was still assembling itself into the structures we now call galaxies. 10 billion light years is not simply far. It is ancient. And the light reaching you from that distance began its journey when the universe was barely a quarter of its current age, before the sun formed, before Earth condensed from dust, before anything familiar existed. Ahead, one point begins to outshine the rest. Not merely brighter, but unnaturally intense. A beacon cutting through the cosmic web. And even from this distance, it refuses to blend into the background, as though the early universe briefly produced something disproportionate to everything around it. The surrounding galaxies fade into context, and scale shifts again, because whatever lies ahead is not just another galaxy, not just another cluster, but a concentration of energy so extreme that it announces itself across billions of years without needing to be resolved. A single point bright enough to dominate an epoch. At this distance, it is still only a dot, yet already it changes the balance of the sky. and the emptiness around it begins to feel less like silence and more like space, waiting for something enormous to be understood. That point of light does not resolve into a galaxy the way you expect, because even as we move closer, it refuses to spread into a spiral or a cluster, remaining compact, unnaturally concentrated, a source whose brightness seems detached from its apparent size. And this mismatch is the first clue that what you are looking at is not starlight in the ordinary sense, but something far more extreme. Astronomers once made the same mistake, cataloging objects like this as faint blue stars, assuming they were small and nearby, until spectroscopy revealed spectral lines stretched toward the red by enormous amounts, a signature of cosmic expansion showing that these points were not local at all, but billions of light years away, which meant the light reaching us had traveled since the universe was young. And if something appears star-like at that distance, it must be unimaginably luminous. This object is TON 618, first recorded as an unremarkable entry in a sky survey, one more blue dot among thousands, but later recognized as a quasar, a beacon powered not by stars but by matter falling into a black hole, so massive it pushes the limits of what structure formation should allow. At its center lies a black hole containing roughly 66 billion times the mass of the Sun, a number so large it stops behaving like an intuitive quantity and instead becomes a gravitational scale. Something that reshapes the surrounding universe simply by existing. If you place this black hole where the Sun sits, its event horizon would extend far beyond the orbit of Pluto, enclosing the entire solar system within a region from which nothing could escape. And yet even that comparison fails to capture its true influence, because what dominates is not just its size, but the energy released as matter falls toward it. The luminosity of TON 618 reaches about 140 trillion times the brightness of the Sun, making it one of the most radiant objects known. And this is not light from stars, but radiation generated as gas spirals inward, heating to extreme temperatures before disappearing across the event horizon. The surrounding galaxy becomes almost irrelevant in comparison, overwhelmed by the central engine, so that the quasar appears as a brilliant core whose output rivals entire galaxies containing hundreds of billions of stars. When this light began its journey toward us, the Sun did not exist, Earth had not formed, and the Milky Way itself was still evolving, meaning what you see now is not the object as it is today, but as it was more than 10 billion years ago. A snapshot from an era when black holes grew rapidly and the universe was more violent than it is now. Even Sagittarius A, the supermassive black hole anchoring the Milky Way with its 4 million solar masses, feels modest in comparison, because TON 618 outweighs it by more than 10,000 times, turning what we normally call supermassive into something almost ordinary by contrast. As we approach further, the brightness intensifies without revealing a solid surface. Only a blazing region where gravity converts motion into heat and heat into radiation, a process so efficient that a relatively small amount of infalling matter can outshine entire stellar populations. The quasar no longer appears as a distant curiosity, but as a dominant presence, a gravitational furnace operating on scales that blur the distinction between object and environment. Its energy flooding surrounding space, ionizing gas, and shaping the region around it long before any structure becomes visible, even from afar. It alters the balance of the cosmic web, not by size alone, but by the intensity of its output. A reminder that in the early universe, a single black hole could rival the combined light of galaxies still in the process of forming. The closer you look, the less it resembles anything familiar. because this is not merely a large object, but a system where gravity, motion, and radiation interact at levels that push beyond ordinary astrophysical intuition. And the more precisely you measure it, the more it feels like an outlier, a structure assembled at the very edge of what the universe appears willing to produce. As we move closer, the point of light expands into structure, and what once seemed like a single source resolves into a vast rotating system, a disk of gas and plasma stretching thousands of astronomical units across its outer edges, calm only by comparison, glowing dull red where temperatures reach a few thousand degrees. Similar to stellar surfaces, while material drifts inward under gravity, slowly at first, orbiting at hundreds of kilometers per second, but this calm does not last, because every step inward deepens the gravitational well, and the disk transforms from a rotating cloud into a furnace where orbital speeds climb into thousands of kilometers per second. Friction emerges between neighboring layers moving at different velocities, and gravitational energy converts into heat with ruthless efficiency. Gas becomes ionized, electrons stripped from atoms, turning the disk into plasma threaded by magnetic fields that twist and amplify as charged particles spiral through them. And these fields do not simply exist quietly, but actively reshape the flow, transporting angular momentum outward, allowing matter to fall inward, creating turbulence that breaks any illusion of smooth rotation. The disk churns not as a uniform ring, but as a dynamic environment filled with instabilities, shocks, and magnetic reconnection events that release sudden bursts of energy, flares that ripple through the plasma like storms in a luminous ocean, each eruption briefly altering brightness before the system settles back into its restless equilibrium. Moving inward further, temperatures climb into hundreds of thousands, then millions of degrees, and the radiation shifts from visible light into ultraviolet and X-rays. The disk now shining, with energies capable of ionizing surrounding gas across vast distances. Material accelerates to significant fractions of light speed, and relativity begins to shape what we see, not as an abstract correction, but as a visible asymmetry. One side of the disk brighter, because it moves toward us, its light compressed and intensified, while the opposite side dims, stretched by motion away from us. This relativistic beaming creates a luminous imbalance that changes as the disk rotates, turning geometry into shifting brightness patterns. Closer still, gravity itself bends light, allowing us to see portions of the disk that should be hidden behind the black hole, forming a warped ring of emission encircling darkness, an effect of space-time curvature that makes the system appear layered and distorted, as though the disk folds around an invisible center in the innermost regions within only a few astronomical units of the black hole. Conditions become extreme beyond comparison with ordinary astrophysical environments. Temperatures rising to billions of degrees, hotter than stellar cores, while matter orbits at 30 to 50% of light speed, completing rotations in days or even hours, depending on radius. This is the innermost stable circular orbit, the final region where matter can circle without immediately plunging inward. And here, energy release peaks because material has descended deepest into the gravitational well, converting maximum potential energy into radiation before crossing the event horizon. Magnetic fields in this region tangle violently, generating jets of plasma and unpredictable variability, and the disk no longer resembles a structured flow but a chaotic boundary between orbit and infall. Photon densities become so high that high-energy photons collide, briefly creating electron-positron pairs before annihilating again, turning radiation itself into a dynamic medium where matter and energy constantly interchange. The entire structure operates as a machine converting gravitational motion into light with extraordinary efficiency, each ring of plasma feeding the next, each instability redistributing momentum, and every inward step amplifying energy release. The closer matter approaches the black hole, the faster it moves, the hotter it becomes, and the more violently it radiates, until the disk appears less like an object and more like a layered cascade of energy flowing toward a boundary that cannot be crossed in reverse. Rotation, turbulence, magnetism, and relativity all merge into a single system that resists simplification. And the deeper you examine it, the less it resembles a disk in the ordinary sense, becoming instead a luminous instability wrapped around gravity. A structure held together only by motion and continuously reshaped by forces that never settle into stillness. The scale of TON 618 raises a question that emerges naturally once the initial shock fades. Because a black hole containing tens of billions of solar masses cannot simply appear fully formed. And the light we observe left when the universe was only about 3 billion years old, meaning this object had a surprisingly short window of cosmic time to assemble itself. The first stars likely formed a few 100 million years after the Big Bang, leaving perhaps less than 3 billion years for a seed black hole to grow into something so immense. And even in a universe filled with gas, gravity does not allow unlimited feeding. As matter falls toward a black hole, it heats and radiates, and that radiation pushes outward on incoming gas, creating a balance known as the Eddington limit, a natural cap on how quickly mass can be added. If accretion proceeds steadily at this limit, growth becomes exponential, with mass doubling every tens of millions of years. And mathematically, such a process can transform a modest seed into a billion solar mass black hole within a billion years. Extending this logic further, reaching tens of billions becomes possible in principle. Yet the calculation assumes uninterrupted feeding, a perfectly steady inflow, and an abundant supply of gas, conditions unlikely to hold continuously in a dynamic young universe. This tension between theoretical possibility and astrophysical realism forces attention toward the environment of the early cosmos, which differed dramatically from the present. Galaxies were smaller, closer together, and far richer in gas. With much of the universe's baryonic matter still unconverted into stars, creating reservoirs capable of sustaining prolonged accretion. Collisions between galaxies were common, and when such systems merged, gravitational torque stripped angular momentum from gas clouds, funneling enormous amounts of material toward central regions where black holes resided. Each merger not only delivered fresh fuel, but also combined black holes themselves, producing larger masses in sudden steps rather than slow accumulation. In this picture, growth becomes a sequence of bursts. Accretion episodes ignited by mergers, followed by quieter intervals. Then renewed feeding when another interaction reshapes the galaxy. Another possibility lies in the nature of the initial seeds. Instead of forming from ordinary stellar remnants of tens or hundreds of solar masses, some black holes in the early universe may have emerged from direct collapse of massive gas clouds, bypassing star formation entirely under special conditions. When cooling is inefficient and fragmentation suppressed, enormous clouds of primordial hydrogen and helium could collapse into black holes containing tens of thousands or even hundreds of thousands of solar masses, providing a head start that shortens the path toward ultramassive scales. Once such a seed exists in a gas-rich region, sustained accretion combined with occasional mergers could drive rapid growth, especially during the epoch when galaxies were still assembling. The quasar era, roughly 1 to 4 billion years after the Big Bang, appears to mark the peak of this activity. Observations show that bright quasars were far more common then than today, suggesting that supermassive black holes across the universe were feeding vigorously at the same time. Gas flowed inward, accretion disks shone intensely, and radiation from these active nuclei began to influence their surroundings, heating gas, driving winds, and eventually limiting further growth. This feedback creates a self-regulating cycle. The more a black hole feeds, the more energy it releases, and that energy can push away the very material needed to continue accretion. Over time, galaxies exhaust their gas or expel it. Star formation declines, and quasars fade, leaving behind massive black holes that persist long after their luminous phases end. In the case of TON 618, the available evidence suggests a convergence of favorable conditions, a massive early seed, repeated merges in a dense protocluster environment, and sustained accretion during the quasar era when fuel was abundant. Such alignment of factors would allow growth to extreme scales within the limited time available. Yet even this explanation retains uncertainty because each mechanism involves assumptions about gas dynamics, merger rates, and accretion efficiency that remain under active investigation. The object, therefore, stands not only as an example of successful black hole growth, but also as a constraint on models of cosmic evolution, indicating that under certain circumstances, the universe can assemble gravitational structures far larger than typical galaxies' central engines, compressing billions of solar masses into a region whose existence reflects both the abundance of early cosmic fuel and the limits imposed by the very radiation produced as that fuel is consumed from several light years away. The quasar no longer appears as a distant beacon, but as a dominant presence, a single source, bright enough to outshine entire stellar fields. And even at this distance, the environment begins to change, because the radiation pouring outward is not gentle starlight, but a flood of ultraviolet and X-rays, capable of ionizing atoms across vast volumes of space. The surrounding region fills with hot plasma as photons strike neutral gas, knocking electrons free and heating matter to millions of degrees, creating a luminous bubble extending outward for light years. A sphere shaped not by physical boundaries, but by energy density. As we move closer, the intensity rises rapidly, not gradually, but exponentially. And at roughly 1 light year, the flux rivals the sunlight received on Earth, except the spectrum is far more dangerous, dominated by high-energy radiation that would strip atmospheres, damage electronics, and sterilize unprotected surfaces. Space itself seems saturated with photons, each square meter intercepting more energy than entire stars produce. And the idea of empty vacuum becomes misleading because radiation now defines the environment more than matter does. Approaching to light-month distances, the quasar begins to resolve into a disk, no longer a point, but a structured system, a luminous plane rotating around a central darkness. The outer regions glow orange and red, while inner layers shift to white and blue, forming a gradient of temperature that traces the gravitational descent of matter, and the disk appears textured rather than smooth, mottled with bright patches where gas density increases and darker lanes where turbulence redistributes material. Flares erupt unpredictably as magnetic fields reconnect, releasing stored energy, momentary flashes that ripple outward through the plasma. If jets emerge from the poles, they appear as narrow beams extending perpendicular to the disk. Searchlights cutting across intergalactic space, their scale measured not in astronomical units but in thousands or millions of light years. Within light weeks, Motion becomes perceptible, the disk rotating fast enough that inner regions shift visibly over hours or days. Differential rotation stretching features into spirals that shear and dissolve, replaced by new structures shaped by turbulence. Radiation now becomes overwhelming, and photon densities rise high enough that photons interact with each other, producing electron-positron pairs in brief flashes of matter and antimatter, which annihilate moments later, returning energy to light. This continuous conversion creates a dynamic medium where energy behaves like a fluid, and the distinction between radiation and plasma begins to blur as we draw nearer still. Relativistic effects reshape the entire view. The side of the disk moving toward us, brightened by Doppler, boosting, its light compressed into higher energies, while the receding side dims and reddens, producing a stark asymmetry. Gravity bends light from behind the black hole, forming a distorted ring that wraps around the central shadow, allowing us to see regions that should be hidden, the disk appearing doubled and warped by space-time curvature at distances of light days. The structure dominates the sky, the central darkness encircled by a luminous halo, where photons orbit briefly before escaping, and orbital velocities approach significant fractions of light speed. Material here is unstable, each orbit a temporary delay before infall, and slight perturbations send gas spiraling inward across the event horizon. The transition is not marked by a surface, but by geometry, the point where escape becomes impossible. Yet from outside, it appears as a boundary outlined by bending light and shifting brightness. The closer we move, the more the universe behind us compresses into a shrinking patch of sky. Gravitational lensing, concentrating distant stars into arcs and rings. Ahead, the shadow expands, not as an object, but as an absence, a region defined by trajectories that no longer return. Radiation continues to stream outward. Motion continues inward. And between these opposing flows lies a narrow zone where matter completes its final rotations, shedding energy in bursts before disappearing into a region that absorbs everything without reflection. Crossing the event horizon does not resemble impact or collision because there is no surface to strike, only a boundary defined by space-time itself. And from a local perspective, nothing dramatic announces the transition. No flash, no jolt, only continued freefall as the geometry around you changes in ways that cannot be sensed immediately. The black hole's immense size makes tidal forces at the horizon surprisingly gentle, far weaker than those near smaller stellar mass black holes. So the crossing can occur without immediate destruction, and for a moment it seems as though nothing fundamental has changed, except that every possible future path now curves inward. Light from the outside universe still reaches you, and looking back, the cosmos appears compressed into a bright, shrinking region behind, warped by gravitational lensing into arcs and rings, colors shifting toward blue as incoming radiation gains energy falling into the gravitational. Well, the external universe accelerates in appearance, distant events seeming to unfold more rapidly, while your own motion continues quietly toward the interior. Signals you emit outward fail to escape, bending back toward the center, not because something pulls them in, but because space-time itself offers no route outward. Deeper inside, the radial direction becomes unavoidable. Not a place you move toward, but a moment you approach. And the singularity lies ahead in time rather than in space. A future event that cannot be avoided any more than tomorrow. Tidal forces begin to grow, first subtly, then increasingly noticeable, the difference in gravitational pull between head and feet stretching objects lengthwise while compressing them sideways. This effect intensifies gradually, not instantly, because the enormous mass spreads curvature over a vast region, yet the increase is relentless, and the geometry that once felt smooth begins to deform anything extended. Matter elongates, structures weaken, and eventually the stretching exceeds the strength of chemical bonds, breaking molecules apart, then atoms, and finally reducing matter to streams of particles drawn along converging trajectories. The process is not violent in the explosive sense, but inevitable, a geometric consequence of falling toward a region where curvature steepens continuously as the descent continues. Space-time distortion dominates perception, paths of light bending inward. The concept of direction losing meaning as all routes lead deeper, and the singularity approaches as a limit where classical descriptions cease to apply. According to general relativity, density and curvature increase without bound, forming a point where equations produce infinities and predictive power fails, indicating that the theory, successful everywhere else, cannot fully describe this regime. Quantum effects should become significant, yet no complete theory uniting quantum mechanics with gravity exists to explain what replaces the singularity. Some proposals suggest a finite region where quantum pressure halts collapse. Others envision a transition to new space-time configurations, but none has observational confirmation. Inside the horizon, such questions remain theoretical because no information returns to test them. Time toward the singularity is finite, measured in hours or days for an ultramassive black hole, long compared to smaller ones but still limited. And during that interval, everything continues to move inward along trajectories dictated by curvature alone. The outside universe fades from view, compressed into a dim patch as blue-shifted light intensifies briefly before disappearing. And the interior becomes dominated by the geometry itself. No stable orbite, no escape routes, only converging paths. In the final stages, tidal forces diverge rapidly, stretching any remaining structure beyond coherence, and the notion of extended objects dissolves into streams aligned with the inward direction. What lies beyond the point where curvature diverges remains unknown, because current physics offers no consistent description, leaving the interior as a boundary between established theory and unresolved questions, a region where space-time continues mathematically but interpretation ends. Ton 618 is not only an extreme object, but a marker in cosmic history, because its existence fixes a moment when the universe was young, dense with gas, and still assembling large structures. And the light we observe today preserves that era, in which supermassive black holes grew rapidly and shone as quasars across enormous distances. During this quasar epoch, galaxies were still forming through mergers. Clouds of hydrogen and helium flowed inward under gravity, and central black holes converted that inflow into radiation powerful enough to reshape their environments. Energy released from accretion heated surrounding gas, ionized entire regions, and drove winds capable of removing the very material needed for further growth, creating a feedback loop in which black holes both depended on and limited the supply of fuel. This self-regulation explains why the most massive galaxies today appear quiet and dominated by old stars, their central black holes no longer feeding at the rate seen in the early universe, their luminous phases long finished. Ton 618 therefore represents not only a massive black hole, but a snapshot of a transitional period when growth and suppression occurred simultaneously, when the same process that built extreme objects also began shutting them down. Observationally, such quasars function as beacons illuminating the space between galaxies. because their light travels across billions of years, passing through intervening gas that imprints absorption features on the spectrum. By studying these lines, astronomers reconstruct the distribution of matter in the early universe, mapping chemical enrichment, density variations, and the evolution of cosmic structure. The quasar's brightness allows measurements impossible with ordinary galaxies, turning it into a probe of environments far beyond its host. At the same time, the mass of its black hole constrains models of structure formation, requiring scenarios capable of assembling tens of billions of solar masses within a few billion years. This pushes theories of accretion, merger rates, and seed formation toward their limits, forcing adjustments in simulations of early galaxy evolution. Each such object therefore influences not only its immediate surroundings, but also the theoretical framework used to describe how the universe develops from near uniformity into complex hierarchies of clusters and galaxies. Future observations promise to refine this picture. Infrared telescopes can attempt to resolve the host galaxy hidden behind the quasar's glare, revealing star formation rates and gas content, while X-ray observatories probe the innermost accretion regions where relativistic effects shape emission. Radio arrays trace jets and outflows extending far beyond the galaxy, mapping how energy from the central black hole propagates into intergalactic space. Gravitational wave detectors planned for coming decades may observe mergers involving similarly massive black holes. Measuring their masses and spins directly from space-time oscillations, offering independent checks on growth scenarios, these approaches combine electromagnetic and gravitational information, gradually building a more complete description of how ultramassive black holes form and evolve. Placed within the broader timeline of the universe, Con 618 occupies a brief luminous phase because quasars eventually fade as gas supplies diminish and feedback halts accretion. The black hole likely remains today at the center of a massive elliptical galaxy surrounded by old stars and little active star formation, its extreme brightness gone but its mass preserved over cosmic timescales. Even such enormous black holes slowly lose energy through Hawking radiation, a process so gradual that evaporation requires durations far exceeding the current age of the universe. During the stelliferous era, galaxies continue evolving, stars form and die, and black holes merge, but far in the future, when star formation ceases and galaxies disperse, ultramassive black holes become among the last remaining structures. Their persistence extends across timescales so large that conventional comparisons lose meaning. Yet even they are temporary within an expanding universe moving toward equilibrium. Understanding TON 618 therefore links multiple scales at once. From the dynamics of plasma near an event horizon to the growth of galaxies and the long-term evolution of cosmic structure, the object embodies how gravity organizes matter into extremes, how radiation feeds back on its environment, and how observation across distance becomes observation across time. The light that left this quasar billions of years ago arrives as evidence of processes already completed, allowing reconstruction of events no longer occurring, and the interpretation of that light depends on theories developed from local experiments and mathematical models. Through this chain, a distant quasar becomes part of a coherent narrative describing how the universe builds, transforms, and ages, not as a static backdrop, but as a system evolving under physical laws that operate consistently across scales.